Jai Hind, everyone. I am from Indian Space Team. Today's we discuss about, have you ever wondered why Earth appears round, yet it isn't a perfect sphere? Well, our planet's shape is a result of a delicate balance between gravity and rotation, a concept known as hydrostatic equilibrium. Essentially, gravity pulls everything towards the center, while Earth's rotation creates a centrifugal force that pushes everything outward. The result of these two forces interacting is a spherical shape, but Earth isn't a perfect sphere. It's an oblate spheroid, meaning it's slightly squashed at the poles and bulges at the equator. This is because of the centrifugal force caused by Earth's rotation, which is strongest at the equator. This makes the Earth's diameter at the equator 43 kilometers longer than its diameter at the poles. Now, let's talk size. With an average diameter of 12,742 kilometers, Earth is the fifth largest planet in our solar system. It's dwarfed by gas giants like Jupiter and Saturn, but it's the largest of the terrestrial or rocky planets. This size is part of what makes Earth's diverse ecosystems and climate possible. However, even within this vast size, there are local variations in Earth's shape. The highest point above sea level, Mount Everest, only lengthens Earth's average radius by 0.14%. Conversely, the deepest point below sea level, the Mariana Trench, shortens the radius by 0.17%. These variations are tiny in the grand scheme of things, but they create the diverse landscapes we see on our planet, from towering mountain ranges to deep ocean trenches. So, Earth's shape is a delicate balance of forces and variations. It's more than just a sphere. It's an oblate spheroid with a dynamic surface that shifts and changes over time. And that's just the beginning of what makes our planet so fascinating. So, while Earth may appear round, it's more of a slightly squashed sphere, with a bit of extra girth around the middle. Beyond its overall shape, Earth's surface isn't smooth. It has mountains, valleys, and deep ocean trenches. But how much do these affect Earth's shape? Let's delve into this fascinating topic. Earth's surface is a rich tapestry of topographic variations. It features the deepest ocean trenches, like the Mariana Trench, which plunges nearly 11 kilometers below sea level, and towering peaks such as Mount Everest, which soars almost 9 kilometers above local sea level. These are the extremes of Earth's topography, and they are certainly impressive, yet they affect Earth's overall shape only minutely. To put it into perspective, the Mariana Trench's depth shortens Earth's average radius by a mere 0.17%, while Mount Everest's height lengthens it by just 0.14%. So despite their awe-inspiring scales, these extreme variations barely make a dent in Earth's overall shape. This isn't to say that all of Earth's surface is static. Quite the contrary, the ocean exhibits what is known as dynamic topography. Unlike the relatively rigid land topography, the ocean's topography is more fluid and changeable. This dynamic nature is influenced by an array of factors, including ocean currents, winds, and tides, all of which contribute to the ceaseless ebb and flow of the ocean's surface. The most distant point from Earth's center isn't the summit of Mount Everest. It's actually the top of the volcano Chimborazo in Ecuador. This is due to Earth's equatorial bulge, a result of its rotation, which means its surface is farthest from its center at the equator. So whether we're talking about towering mountains, deep ocean trenches, or the bulging equator, Earth's surface is far from smooth. But it's these variations, from the minute to the extreme, that make our planet so fascinating and diverse. They provide the landscapes we explore, the seas we sail, and the mountains we aspire to climb. Despite the impressive heights of mountains and depths of ocean trenches, they barely make a dent in Earth's overall shape. But they do a whole lot in making Earth the diverse and beautiful planet we call home. If you could smooth out all the oceans, what shape would Earth be then? Allow me to introduce you to the world of geodesy and the concept of the geoid. Geodesy is the scientific discipline dedicated to understanding Earth's geometric shape, orientation in space, and gravity field. It's like Earth's own personal biographer, charting its physical characteristics and changes over time. One of the key concepts in geodesy is the geoid, an imaginary surface that extends over the entire Earth without being affected by mountains, valleys, or other irregularities. Imagine pouring water over the entire Earth, with no land masses to interrupt its flow. This water would settle into a shape solely influenced by Earth's gravity and rotation. This shape is what we call the geoid. It's important to note that the geoid isn't a perfect sphere. Due to Earth's rotation, it bulges slightly at the equator and flattens at the poles, making it an oblate spheroid. But the geoid isn't just about the shape of the Earth. It's also a crucial tool for measuring Earth's topography. When geodesists measure the elevation of a mountain, for instance, they're not measuring from the actual sea level, they're measuring from the geoid. This is because the sea level is a dynamic and ever-changing surface, influenced by tides, winds, and other factors. The geoid, on the other hand, is a stable, consistent reference surface. In essence, the geoid serves as the world's sea level. It paints a picture of an Earth unmarked by topographical features, providing a level playing field for geodesists to carry out their measurements. It's the reference point from which we measure the height of mountains, the depth of ocean trenches, and the variations in Earth's topography. So, when we talk about sea level, we're actually referring to this idealized shape, the geoid, rather than the actual bumpy surface of the ocean. Ever wondered what lies beneath your feet? Let's delve into the composition of Earth's crust. The crust is like Earth's outer skin, a layer of rock that envelops our planet, and it's divided into two key types, oceanic and continental. Oceanic crust sits beneath the ocean floor and is predominantly composed of basalt, a type of rock that forms from rapidly cooling lava. It's relatively thin but dense, typically extending about 5 miles deep. On the other hand, continental crust forms the continents in the areas of shallow seabed close to their shores, known as continental shelves. It's thicker but less dense than oceanic crust, extending from 25 to 45 miles deep. Continental crust is composed of many rock types, including granite, sediments, and metamorphic rocks. Interestingly, nearly 75% of the continental surfaces are covered by sedimentary rocks, despite these forming only about 5% of the crust's mass. Now let's talk about the lithosphere. Imagine the crust and the uppermost part of the mantle combined. That's the lithosphere. It's a rigid, rocky outer layer that's divided into massive pieces called tectonic plates. These plates float on a semi-fluid layer of the mantle, and their movement shapes Earth's surface over time. Speaking of surfaces, Earth's topography is incredibly varied, both on land and beneath the ocean. The land surface features mountains, valleys, plains, and more, while the submarine terrain of the ocean floor is equally diverse, boasting underwater mountains, trenches, and vast plains. The average depth of the ocean floor, or bathymetric depth, is about 4 kilometers. Despite being underwater, it's as varied as the terrain above sea level. The ocean floor and the land surface together form the top of Earth's crust, painting a dynamic picture of our planet's physical characteristics. So whether you're standing on a mountain peak or diving in the deepest ocean, you're exploring the fascinating topography of Earth's crust. Earth's surface isn't static, it's constantly changing thanks to the movement of tectonic plates. Imagine Earth's crust and upper mantle as a jigsaw puzzle of rigid segments. These pieces, known as tectonic plates, aren't fixed in place. Instead, they're continuously moving, albeit at a pace slower than the growth of your fingernails. This movement is driven by the heat deep within Earth's core, causing a phenomenon we refer to as plate tectonics. Now, these tectonic plates don't just move in a random fashion. They interact at specific boundaries, and it's these interactions that shape our planet's surface. There are 3 types of boundaries: convergent, divergent, and transform. At convergent boundaries, 2 plates collide. This can result in one plate being forced beneath the other, a process known as subduction. This is where some of the world's most dramatic landscapes are formed, such as towering mountain ranges and deep-sea trenches. On the other hand, at divergent boundaries, 2 plates move apart. This allows molten rock, or magma, from beneath the Earth's crust to rise, cool, and solidify, forming new crust. This process is responsible for creating mid-ocean ridges, the underwater mountain ranges that wind their way through our oceans. Lastly, at transform boundaries, 2 plates slide past each other horizontally. The friction between the plates can cause earthquakes, which, while potentially devastating, are a natural and essential part of Earth's ever-changing topography. Over millions of years, these plate tectonic processes have sculpted the Earth's surface, creating and reshaping continents, forming mountain ranges, carving out ocean basins, and triggering volcanic eruptions. But remember, this isn't a process confined to the past. Right now, beneath your very feet, the Earth is moving, reshaping, and evolving. Every tremor, every volcanic eruption, every mountain range, and every ocean trench is a testament to our planet's dynamic nature. Share this video, so remember, the ground beneath your feet is part of a dynamic, ever-changing Earth shaped by the relentless movement of tectonic plates.